Hello viewers, welcome to the session on quantum computing. Hope you might have watched my previous video on Introduction to Quantum Computing. In this video, let us discuss about the quantum gates. A quantum gate is a basic quantum circuit operating on qubits. They are the building blocks of quantum circuits like classical logic gates or for the conventional digital circuits. Due to the normalization condition, every gate operation U has to be unitary. That is, product of U transpose is equal to identity. The number of qubits in the input and the output of the gate must be equal. The quantum gates perform logical operations on qubits. Unlike many classical logic gates, quantum gates are reversible. Unlike traditional bits, which can only be 0 or 1, a qubit can exist in a superposition of 0 and 1. This ability to exist in multiple states at once gives quantum computers a tremendous power. Quantum circuits can be used to perform a wide variety of tasks according to the applied quantum algorithms. There are a lot of types of quantum gates. These are single qubit gates, which can flip a qubit from 0 to 1, as well as allowing superposition states to be created. Then there are two qubit gates. These allow the qubits to interact with each other and can be used to create quantum entanglement. Few examples of quantum gates are Hadamard gate, Poly Xgate, Poly Ygate, Poly Zgate, C0 gate. There are lots of types of quantum gates. Let us see each of these in detail. Coming to the single qubit gate, that is poly X gate, the matrix representation is given here and the circuit representation is also shown here. Now, once a single qubit is applied to this X gate, it gets inverted. That is, it behaves like a classic NOT gate. You can see this operation. You can perform the operation of in the X gate, you can see that the ket 0 has been converted into ket 1. And similarly, the ket 1 is converted into ket 0. Next, coming to the poly Y gate, there is no classical equivalence of this gate. And here it shows the matrix representation, the circuit representation of poly Y gate. And coming to the poly Z gate, it does the phase shift. Next comes the Hadamard gate. And the unitary matrix representation of the Hadamard gate is H is equal to 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. And this is the circuit representation. And here there is no classical equivalent, but it is a most important gate for quantum computing. And this gate is used to put qubits into superposition. Now, once the gate 0 is applied to the Hadamard gate, it gives the result of two states in the superposition. And the the Hadamard gate, once applied again, it will lead to the output of gate 1. Hence, two Hadamard gates used in succession can be used as a NOT gate. Next, we will see about the control NOT gate. And this gate operates on two qubits. And the two qubits are the control and the target bit. And according to the logic, if the control bit is 1, the target bit is inverted. You can observe in the table, if the control bit is 1, the input 0 bit is inverted to 1. See here, so the CN gate has similar behavior to the XOR gate with some extra information to make it reversible. And here is the example operation of multiplication by 2. We can build reversible logic circuit to calculate by multiplication by 2 using the same gates arranged in this following manner. Next, we will see about the control NOT gate. A gate which here there are two control bits and one target bit. And the logic behind is when two control bits are 1, the target bit it is inverted into. Observe in this table, when two control bits are 1, the 0 input bit is being inverted. Similarly, this row. And the operations on the qubits should be a reversible one. Here, if you see this type of gate like NAND gate which is not reversible cannot be used. So we must use only the quantum gates in the quantum circuits. Here is the universal quantum gate That is, CCN is considered to be the universal reversible logic gate and it can be used as an AND gate. Here is an example of quantum circuits. And you can see here each of these represents a single qubit and all of this represents the gates. And some of the gates are with the one qubit and the other are with the multiple qubits. And this double line represents the classical bit. The number 2 means there are two classical bits. And this shows the measurement gates. When we measure the qubits, they collapse to either 0 or 1, which store in the classical bits. So the logical gates can be arranged to build the quantum circuits. A quantum circuit made up of Hadamard gates with 3 qubits has been shown in this example. Now let us see why quantum algorithms. What makes the quantum algorithm potentially faster than the classical one? The first thing is quantum parallelism. By using superposition of quantum states, the computer is executing the algorithm on all possible inputs at once. The next one, the size of the state space for the quantum system is exponentially larger than the corresponding classical system. The next feature is the entanglement capability. Different subsystems in a quantum computer becomes entangled exhibiting non-classical correlations. So, with the use of quantum algorithms, it is possible to solve problems on quantum system much faster than the classical computer. Few examples are factoring and searching, so where quantum algorithms are known very fast than the classical ones. And some of the implications are cryptography and information security. See you in my next video. Have a happy learning. Bye bye.